Hello viewers, my name is Dr. Ajay, Associate Professor, Department of ECE, Institute of Aeronautical Engineering College, Hyderabad. Today we are going to discuss the topic on definitions and terminology of Module 1, that is the antenna basics. So today's topic is antenna basics, which comes under Module 1 of our course, Antennas, Waves and Propagation. Let us start our session. So here, what is actually an antenna? So let us see some basic definitions and basic parameters of an antenna. Here, whenever we are going to design an antenna, we need to check the performance of the antenna. So to check the performance of the antenna, we need to know the characteristics or the parameters and the definitions of the antenna. So here, we'll see in this module, that is the basic definitions of antenna. So the basic definition of an antenna is, here an antenna, it is simply a metallic rod which is used to generate electromagnetic waves. So an antenna, it is a metallic rod which produces electromagnetic waves. And here these antennas are much more simple devices connected to every radio. So here the radio waves and the electromagnetic waves are both similar, both are having the same meaning. So these are the transducers that convert the voltage from a transmitter into a radio signal. So whenever a transducer, it is a device which converts one form of energy into another form of energy. So one form of energy is being converted into another form of energy. So this is another definition for an antenna. So here in this figure, you can see here, there will be a transmitting antenna, a wireless communication system. To establish, we need a transmitting antenna, we need a generator, we need a receiving antenna, and we need a receiver. See, these are the four devices which we to establish a wireless communication system. Here, when we must give the signal to the transmitting antenna, so we are going to give an electrical signal to the transmitting antenna. So this transmitting antenna will convert this electrical energy into radio energy. Here, this electrical energy is being converted into radio energy. Hence, the name is given as a transducer for an antenna. So they pick up radio signals out of the air and convert them into a voltage for recovery in a receiver here. A radio wave, it is a combination of a magnetic field at a right angle to an electric field. So generally, the radio waves produced by an antenna are known as transverse electromagnetic waves, TEM waves. Here, the radio waves which produce the fields are electric field and the magnetic field. This electric field and the magnetic field both are perpendicular to each other. And this electric field and the magnetic field are also orthogonal to the direction of propagation of the wave. Hence, these radio waves produced by antenna, we can call them as TEM waves. We can call them as TEM waves, transverse electromagnetic waves. So, what about the electromagnetic waves produced by an antenna? These both are perpendicular to each other and also orthogonal to the direction of propagation of the wave. Hence, the name is given as TEM waves. The waves that are produced by an antenna will radiate into free space and they travel with a velocity of light, that is 3 into 10 power 8 meters per second. With the speed of light is 3 into 10 power 8 meters per second here. The radio wave, it is a combination of magnetic field at right angle to an electric field. You can see here, these are electric lines of force and these are magnetic lines of force where E and H both are perpendicular to each other. So these are some of the basic definitions of an antenna. A metallic device in the form of wire or rod used for radiating or receiving radio waves. We call it as a definition of antenna. So whenever a high frequency current is applied to a conductor, some amount of energy resides inside the conductor in the form of resistance. Some amount of energy will be escaped into the free space. So this energy that is escaped into the free space, we call it as a radio wave. We call it as electromagnetic energy or electromagnetic waves. So here, the transducer which converts radio frequency electrical current into an electromagnetic wave of the same frequency as that of an electrical current. So this is another definition. So there are three basic definitions for an antenna. One is, it is simply a wire or rod for receiving radio waves. It is a transducer which converts one form of energy into another form of energy. An antenna acts like a coupling device between a generator or transmitter in free space. So in other words, an antenna, it is an impedance matching device between the free space and the transmission line here. So here we can also call an antenna as an impedance matching device. So why? Because the impedance of the free space differs from the impedance of the wire. So we are going to give input line. This is the coaxial cable. On here there is a transmitting antenna here, and this is the free space. The impedance of free space is 377 ohms. Suppose let us say the impedance of cable is 75 ohms. So there is an impedance mismatch. So there is an impedance mismatch between the cable impedance and also the free space impedance. Hence what we are going to do is to deliver maximum amount of power between the transmitter and the free space, we need to match the coaxial cable impedance with respect to the free space impedance. So we need to design the antenna in such a way that the impedance of the cable will be exactly equivalent to the impedance of the free space, so that more amount of energy can be radiated by the antenna. So here antenna, it's also an impedance matching device here. Next, the another definition for antenna parameters, it is isotropic radiator. So what is an isotropic radiator? It is also known as a point source. So it is the another definition, another name given for the isotropic radiator is isotropic source. The best example for an isotropic source is point source. A radiator which radiates uniformly in all directions, we call it as an isotropic radiator. So suppose this is an antenna or an isotropic source, it radiates uniformly in all directions. Hence the name is given as isotropic radiator. It is a lossless radiator, hence it is used as a reference antenna. As this radiator, it is a lossless radiator, hence it is used as a reference antenna. So point source is the best example for an isotropic radiator. The isotropic radiation is nothing but the omnidirectional radiation. We can also, in the two-dimensional representation and three-dimensional representation, we can represent the radiation pattern of isotropic radiator. So here it is a figure of 8 in 2D. It will be as a figure of 8 in two-dimensional. In three-dimensional, it will be dot net shaped like this. In three-dimensional, the isotropic source radiation pattern will be in dot net shaped. So this is the dot net shaped, and this is the two-dimensional representation of the radiation pattern of an isotropic radiator. Now here let us go define another two important parameters of an antenna, radian and steradian. So we know that theta is equal to arc by radius. So this is theta represents the angle. Theta represents an angle. The arc subtended to the radius, we call it as an angle. So 1 radian, the units of angle is radian. The units of angle is radian here. So 1 radian is defined as the plane angle with its vertex at the center of a circle of radius r that is subtended by an arc whose length is r, as shown in the figure. So here there is a circle here. This is the center. There is a circle here. In the circle, some angle it is subtended on the circle here. Let us define this as an arc of the circle. Arc of the circle whose length is r here. Whose length is r. Let us assume this the radius of the circle is r. So we know that theta is equal to arc by radius. So theta is equal to arc by radius. So theta is equal to arc length, it is r, and the radius is also r. This is equal to 1. So this is 1 radian here. This is 1 radian here. So here how many radians are there in a complete circle? So here we can say here theta is equal to arc by radius here. So this is equal to arc means arc length means the total circumference of the circle is 2 pi r by r get cancelled. Theta is equal to 2 pi radians here. So 2 pi radians here. A complete radian will be having 2 pi radians here. And the another angle, another parameter of an antenna is steradian. So here the measurement of a solid angle, the units for a solid angle is steradian. So we are having two different types of angles for our antennas and wave propagation. One is plane angle and the solid angle. For the plane angle, we measure in terms of radians, and the solid angle is measured in terms of steradian. So one steradian is defined as the solid angle with its vertex at the center of sphere of radius r that is subtended by spherical surface area equal to that of a square with each side of length r. So here what we are going to do is, suppose there is a beam of light here. So in this beam, total beam is falling, let us assume on this surface. Let us assume a small area here. So with what angle this area is subtended with respect to the point, to a fixed point here. So here, let us assume this as a sphere here. So with what angle this spherical surface is subtended with this point. So we call this angle as a solid angle. We call this angle as a solid angle. So here, whenever there is a beam of light, this is, let us assume the beam, total beam. In this beam, we are going to consider a small area. So in this small area is going to subtend at what angle? We call it as the solid angle. So one steradian is defined as a solid angle with its vertex at the center of a sphere that is subtended by spherical surface area equal to that of a square with each side of length r. So generally d omega is equal to area subtended by r square. So here the area of the sphere is 4 pi r square divided by r square. R square get cancelled. Will be remaining 4 pi steradians. So a solid angle will be having 4 pi steradians here. So these are the angles, the ratio of subtended arc to length of arc to the radius, and solid angle, the ratio of subtended area on sphere to the radius squared. Area by r square here. So area by r square means here 4 pi r square, the radius by r square get cancelled, you will get 4 pi steradians here. The radiation pattern, the basic definition of radiation pattern is it's a graph drawn by taking all the maximum field strengths that have been radiated by an antenna. So radiation pattern, it is nothing but it's a graph that is drawn by taking all the maximum electric field strength at all points surrounding the antennas. We call it as a radiation pattern. So the radiated energy is not of the same strength in all directions. We know that the antenna radiates energy in all directions with a different field strength. So it is measured in different field strength, and this radiated energy is measured in terms of the field strength here. So the unit of radiation pattern is volt per meter. It determines the distribution of radiated energy in space. How much amount of energy is radiated in the free space. It is measured in terms of the field strength here. So radiation pattern, it is nothing but it's a graph which shows the variation in the actual field strength of electromagnetic field at all points which are at equal distance from the antenna. So here this radiation pattern is nothing but it's a graph which shows the variation of actual field strength of the electromagnetic field at all points which are at equal distance from the antenna. So let us assume here there is an antenna here. If this antenna is going to generate radiation in different directions, let us measure what is the field strength here. Assume it as E1. Let us measure the field strength in this direction E2. This is E3, and this is E4, and this is E5. So let us join all these points here. Let us join all these points. This represents the radiation pattern. So we need to find out the field strength at all points surrounding the antenna at equal distance from the antenna. So when we join all those points, the graph that is obtained, we call it as a radiation pattern. And this radiation pattern contains of 4 lobes. One is the major lobe, where the radiation pattern is maximum in one particular direction. So here this is known as the main lobe or the major lobe, where the radiation pattern is maximum, and this is known as the back lobe, and these are known as side lobes here. These are known as side lobes here. So we are having different types of radiation patterns. These can be classified as omnidirectional pattern, pencil beam pattern, fan beam pattern, and a shaped beam pattern here. So omnidirectional pattern, it may be represented in the figure of 8, or we can also represent as a dot net shaped like this. So pencil beam, it is very narrow. So pencil beam represents it is narrow. It is narrow in one direction. You can see here, this is like this. And fan beam pattern. So fan beam pattern where the radiation pattern will be maximum in one direction or minimum in other directions. So a fan beam pattern, it is also known as like this. This is known as a fan beam pattern. It is like it will be the radiation pattern will be like a fan where the radiations will be different in different directions. And here shaped beam pattern. So the radiation pattern that is produced by any antenna will be of any shape. It may be of any shape, right? Hence the name is given as shaped beam pattern, which is non-uniform. Which is non-uniform and known as a shaped beam antenna. Shaped beam antenna here. And here, so these are the radiation pattern. The performance of the antenna is usually described in terms of principal, E plane and H plane. So we are going to draw the radiation pattern. From the radiation pattern, we draw the major lobe, and these are the side lobes, and this is the back lobes, and these are minor lobes. And we are going to align this major lobe with any of the axis, either x-axis or y-axis or z-axis. So we are aligning this, coinciding the radiation pattern maximum with this z-axis here. And here, the angle measured exactly at a half of points of the major lobe, we call it as half power beam width, HPBW. The angle measured exactly at half power points of the major lobe, we call it as half power beam width. Let us assume these 2 points, let us join these 2 points, and here we are going to measure this angle, we call it as half power beam width here. And similarly, the angle measured between the first nulls, so these are known as the first nulls. Null means there is no radiation pattern. Null means there is no radiation pattern. So whenever we are going to draw, we are going to consider some angle between the first nulls or between the first lobes. That angle formation, we call it as beam width between the first nulls. Beam width between the first nulls. So the angle that is taken between the first nulls, we call it as a beam width between the first nulls. So here there are 2 types of planes here. We are having a E plane and H plane. E plane means the plane containing the electric field in the direction of maximum radiation. H plane is a plane containing the magnetic field vector in the direction of maximum radiation. The next parameter is radiation intensity. So here radiation intensity of an antenna, it is closely related to the direction of beam focused and the efficiency of the beam towards the direction. So simply, in simple terms, the radiation intensity is defined as the power per unit solid angle. In simple terms, we can also define it as power per unit solid angle. So here, radiation intensity is denoted by the symbol capital pi, or also we can also represent by the symbol U, power per unit solid angle. Power per unit solid angle. So here the units are watts. Why? Because power is represented in watts per steradian. Unit per solid angle. Why? Because solid angle units are steradian. So watts per steradian. And the another definition for gain is we shall find out the definition of gain. So here gain means gain of an antenna without involving the antenna efficiency, defined as gain is equal to maximum radiation intensity from test antenna by maximum radiation intensity from reference antenna for the same power input. So here the test antenna means a practical antenna. So the antenna that we have designed, the antenna that we are going to test its performance, we call it as a test antenna or the subject antenna. So subject antenna or the test antenna, both are having the same meaning, or the practical antenna. So gain is represented by the symbol G, and gain with respect to the isotropic antenna, we represent it by the symbol G0. We represent it by the symbol G0 here. So gain is defined as maximum radiation intensity from test antenna by maximum radiation intensity from reference antenna for the same power input. If this reference antenna is taken as isotropic antenna, we take the reference antenna as isotropic antenna, because isotropic antenna, it is a lossless antenna. It radiates uniformly in all directions. Hence, it is a lossless antenna. Hence, it is taken as the reference antenna. Now, another definition for gain. So, we can also define in terms of G naught. So, gain with respect to the isotropic antenna. It is the maximum radiation intensity from test antenna by maximum radiation intensity from isotropic antenna for the same power input. So, here make a note that input power must be same for both the antennas. It may be either the test antenna or it may be the isotropic antenna. Input power must be given same for both the cases to determine the value of G naught. So generally, G naught is given by the maximum radiation intensity of test antenna as pi m by pi naught. Pi m by pi naught here. Another definition for gain in terms of power. In terms of power also, we can also define this as maximum power received from given antenna by maximum power received from reference antenna P2 for the same power inputs. Another parameter, the next parameter of antenna performance is directivity. So the directivity is given by defined as the ratio of maximum radiation intensity of test antenna by average radiation intensity of test antenna. So the maximum radiation intensity of test antenna by average radiation intensity of test antenna, we call it as D representation is equal to pi of theta comma pi of max by pi AV. Pi AV. Another definition, next the definition of antenna efficiency. So the efficiency of an antenna, it is also denoted as eta. Efficiency represented by symbol eta. It is defined as antenna efficiency is equal to power radiated by total input power. Power radiated by total input power. So the basic formula to find out the antenna efficiency is WR by WR plus WL. WR by WR plus WL. The next definition is capture area. The capture area, we can also name it as effective area. Effective area or capture area. We call it as the effective area. So the effective area or the capture area or the effective aperture is defined as power received to the Poynting vector of the incident wave. Power received to the Poynting vector of the incident wave, we call it as effective area. And this is, let us assume we have this length of the antenna. So this we call it as the physical length of the antenna. That is the actual length of the antenna. And the portion where the electromagnetic rays fall, we call it as the effective area. Where absorption takes place, we call it as an effective area here. So the basic definition, according to the basic definition of capture area or the effective area, the effective aperture is denoted by the symbol AE. We can also represent it by symbol EA, which is given as W by P here. And here, the ratio of effective area to the maximum effective area is known as effectiveness ratio, which is represented by the symbol alpha. So alpha is equal to AE by AE max here. So the effectiveness ratio, the definition, it can be defined as the ratio of effectiveness area to the maximum effective area. We call it as the effectiveness ratio denoted by symbol alpha, whose value lies between 0 and 1. And similarly, the scattering aperture is also denoted by symbol AS, and loss aperture is denoted by symbol AL. Scattering aperture depends upon the radiation resistance, and loss aperture depends upon the loss resistance. So accordingly, the equations will be modified. W by P. So here we can write as W means I square R. Why? Because it depends upon the radiation resistance of the antenna. Similarly, for this, W is equal to I square RL. I square RL. So accordingly, the equations can be derived for the scattering aperture and the loss aperture. So here the scattering ratio is defined as the maximum scattering aperture and the maximum effective aperture. So here the scattering ratio is defined as the AS by AE. The ratio of the scattering aperture to the effective aperture, we call it as the scattering ratio represented by the symbol beta, whose value lies between 0 to infinity. Whose value lies between 0 to infinity. And the collecting aperture, it is a combination of three. That is the effective aperture, the scattering aperture plus the loss aperture. So the combination of these three collectively we call it as the collecting aperture. The physical aperture of the antenna, it is the actual physical size possessed by the antenna. The actual length of the antenna, we call it as the physical aperture. So in antennas like a horn or parabolic reflector, the physical aperture is of great significance because the design of these antennas is quite large here. So the physical aperture means the actual aperture area, we call it as a physical aperture. The relationship between the maximum aperture and the gain is given by d is equal to 4 pi by lambda square into AE. So for most of the cases, to calculate the value of effective aperture, which is depends upon the directivity of the antenna, which is given by the relationship d is equal to 4 pi by lambda square into AE. So d is equal to 4 pi by lambda square into AE. Now another basic parameter of the antenna is effective length. So effective length is denoted by the symbol LE, which is the ratio of the open circuited voltage to the incident field strength. Symbolically, we can represent it as LE is equal to V by E. So an antenna in the receiving mode or the transmitting mode, whether it is in the form of a wire, horn, aperture, array, dielectric rod, etc., is used to capture electromagnetic waves and to extract power from them or to radiate. So the effective length is given by the symbol V by E here. Now reciprocity theorem. So here the antenna can be used by both. Any antenna can be used as a transmitting antenna and also as a receiving antenna. Hence we are going to apply the reciprocity theorem either in the transmitting mode or the receiving mode. So the statement of the reciprocity theorem states that if an EMF is applied to the terminals of antenna number 1 and current is measured at the terminals of antenna number 2, then an equal current both in amplitude and phase will be obtained at the terminals of antenna number 1 if the same EMF is applied to the terminals of antenna number 2. Another statement is when a current I1 at the terminals of antenna number 1 induces an EMF of E21 at open terminals of antenna 2 and a current I2 at the terminals of antenna 2 induces an EMF E12 at the open terminals of antenna 1, then E12 will be equal to E21 provided I1 is equal to I2. So in most of the cases for both the transmitting and receiving antenna holds good this reciprocity theorem. So this reciprocity theorem holds good for an antenna which acts like a transmitting antenna or the receiving antenna here. So from the applications point of view of the reciprocity theorem, there is a relationship between the power received to the power transmitted. So which depends upon the effective apertures of the transmitting antenna and also the effective apertures of the receiving antenna. It is given by, it is known as a Frisch transmission formula. So the Frisch transmission formula is given as WR by WT is equal to AER by AET by lambda square. So the relationship between the power ratios of the transmitting antenna and receiving antenna is known as the Frisch transmission formula, which is given by WR by WT is equal to AER by AER AET by R square lambda square, where capital R represents the distance between the transmitting antenna and receiving antenna, and lambda is the wavelength, and AE is known as the effective aperture of the transmitting antenna and the receiving antenna. And R, that is the distance between the transmitting antenna. There is a condition which is known as a Fraunhofer condition. So to have we have a clear-cut radiation pattern under this condition only, that is R is greater than 2d square by lambda, where the electromagnetic waves and the electric lines of force and magnetic lines of force both are perpendicular to each other will be in the far region only. So the far region condition is R is greater than 2d square by lambda. So this condition we call it as the Fraunhofer condition. The next parameter is front to back ratio. The front to back ratio is the ratio of power radiated in the front radiation lobe and the power radiated in the opposite direction. We call it as a front to back ratio. So power radiated in the desired direction by power radiated in the opposite direction, we call it as FBR. So FBR stands for front to back ratio, denoted by the symbol FBR. It is measured in dB, and the power radiated in the desired direction by power radiated in the opposite direction, we call it as FBR. So whenever we want to judge the performance of the antenna, we need to check what is the value of the FBR for an antenna. So power radiated in the desired direction by power radiated in the opposite direction. The next parameter is antenna beam width. So beam width, it is aperture angle from where most of the power is radiated. Just now we discussed that there is be a major lobe here. So we are going to consider half power points of the major lobe and join these two lines here. The angle so formed, we call it as half power beam width. Half power beam width. So the angle that is taken at half power points of the major lobe, we call it as half power beam width. Assume here there are two lobes here. Here there is a null here and this is a null here. This is known as first null and this is known as the first null. So the angle taken between these two first nulls, we call it as first null beam width. We call it as a first null beam width here. The next one is antenna beam efficiency. So the antenna beam efficiency is given as the power transmitted within the cone angle by power transmitted by the antenna. So the power transmitted within the cone angle by power transmitted by the antenna, we call it as the beam efficiency. So another definition for beam efficiency is defined as the ratio of main beam area by total beam area. The ratio of the main beam area by the total beam area, we call it as the beam efficiency. Suppose if there is a antenna radiation pattern is like this, this total we call it as the total beam area, and this is the major beam area. This is the major beam area. So major beam area by total beam area, we can also calculate the beam efficiency. On field zones, there are three types of field zones for us. The one is reactive near field zone. The other one is Fresnel region or radiating near field zone. The other one is the far field zone. So when we can call it as a reactive near field zone. So here when the R is less than the distance from the antenna, let us assume this as R here. Suppose this is an antenna. This distance is R. And this is the length here. This is the dimension length of the antenna here. So when R is less than 0.62 root of L cube by lambda, then we call that zone as a reactive near field zone. Here the electric field and the magnetic fields are not formed. The radiation pattern is also not formed here in this region. Hence the name is given as a reactive near field zone here. And the second one is radiating near field zone, where if the R value lies between 0.62 into root of L cube by lambda and 2L square by lambda, L is the length of the antenna, physical length of the antenna. Then under this condition, we call the zone as the radiating zone or the radiating near field zone or Fresnel zone. And when R is greater than 2L square by lambda, then that zone we call it as the far field zone or Fraunhofer zone. So in this zone only, the electric and magnetic fields are perpendicular to each other and also orthogonal to the direction of propagation of the wave, where the radiation pattern and the major lobes are clearly observed in this far field region only. Retarded vector potential. So here, while dealing with the antenna, the finite time of propagation of great importance. Hence, the name is given as retarded vector potential here. Here, we need to calculate the retarded potentials for calculating the E field analysis and H field analysis. We need to consider all the potentials that are going to reach at a distance point. Hence, the name is given as a retarded vector potential, which is denoted by the symbol here, V here. So here there are two types of potentials. One is electric scalar potential. The other one is a vector magnetic potential here. So we are going to calculate E, the electric scalar potential, and also the magnetic vector potential A. Hence the name is given as a retarded potentials. So these are the basic points of the module 1, that is the basic parameters of an antenna here. Let us have a look on the references. You can, for all these basic definitions, you can see John D. Cross, Antennas and Wave Propagation by Bakshi, K.D. Prasad, Antennas and Wave Propagation. So let us close our session today. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.